Hello everyone. In this video, we're going to be learning about regression models with interaction terms. So in the previous video, we saw quadratic models where the marginal effect of a change in the regressor depends on the value of the regressor itself. So when we move to models with interaction terms, we're looking at cases where the partial effect of a particular explanatory variable may actually depend on the magnitude of an other related explanatory variable. This is very new to us now, right? So let's learn about it with an example. So we are back to our housing prices regression. So we're looking at how the house price varies with the square foot of the house, the number of bedrooms in the house. And notice, we now have a third variable, which is square feet multiplied by bedrooms. So you've taken the two earlier regressors, multiplied them to create a third regressor, and that's our third regressor. And then we also have the number of bathrooms in the house. Now, what is this multiplied term? That's what we call an interaction term. And the utility of an interaction term is best served by computing marginal effects or partial effects. So suppose we are interested in how the housing price changes when the number of bedrooms in the house changes. So we're looking at how, if you add more bedrooms to the house, how does it change the housing price? In other words, what I'm doing is I'm taking the partial derivative of this regression function with respect to the number of bedrooms. And if I do that, well, there's a beta 2 that's associated right with bedrooms, so that's going to show up here. And bedrooms also shows up in this interaction term, beta 3 times square feet times bedrooms. So beta 3 is like a constant. Square feet is another variable, which I will treat as a constant when I take partial derivatives. So when I take dou price by dou bedrooms, it's going to be beta 2 plus beta 3 times square feet. So what's this telling us? If you want to look at the effect of an additional bedroom on the price of the house, that depends on how large the house is, the square footage of the house. And that sort of intuitively makes sense, right? If you are at a 2-bedroom house and if you add a third bedroom, that's going to affect prices in a certain way. If you are in a villa and if you're adding an extra bedroom, that's going to affect prices in a slightly different way. So that's what this marginal effect is telling us. So we're going to unpack this sort of, so this is primarily the usefulness of these interaction terms. And we're going to be looking at the particular issue we're concerned about here is how we interpret the numbers beta 2 and beta 3 and how we think about the significance attached to those numbers. So let's think of beta 2. Now, beta 2 is, so if you have dou price by dou bedrooms, that's just going to be equal to beta 2 if say square foot is 0. So if I plug square foot equals 0 here, change in price by change in bedrooms is just going to be equal to beta 2. Meaning, beta 2 gives us the effect of an extra bedroom when the square footage is 0. So beta 2 tells us how the price will change when the number of bedrooms changes, but when the square footage is 0. That is infeasible, right? You can't have 0 square foot and talk about increasing the having an extra room. So this sort of interpretation is what makes things a bit complicated, but we have a workaround solution. What we are going to do is we're going to reparameterize variables, or we're going to redefine the variables in a specific way, which makes our interpretation one step better. How are we going to do that? Let's see. Suppose our original model is given by this expression. You have an x1, you have an x2, and an interaction term x1 times x2. Now we're going to redefine this interaction term in a slightly different way. I want you to focus on this particular term that I'm highlighting right now. I'm going to take x1 and redefine that variable by subtracting the average of that x1 variable. I'm going to call mu1 is the average of that x1 variable. So for every observation in that x1 column, I'm going to subtract that average and create a new variable. That is my x1 minus mu1 variable. Similarly, I'm going to take the x2 variable, compute the average of that x2, and I'm going to call that mu2. Every single observation in x2, from every observation, I'm going to subtract this average mu2. And I'm going to, this difference, I'm going to call it a new variable, x2 minus mu2. So once I've created these new redefined variables, I'm going to use those in the interaction terms. And now my regression equation is rewritten as my intercept is now alpha naught. And I have a delta 1 times x1, delta 2 times x2, plus beta 3 is now associated with an interaction term that looks like this, plus 0. Now, how is this useful? Let's go ahead and figure out dou y by dou x2, and you'll see how it makes sense. If I take the partial derivative of y with respect to x2, well, I'm going to get a delta 2, and that just comes from here. And I'm going to get plus a beta 3 times x1 minus mu. So earlier, before we did this redefining, if I did dou y by dou x2, I'll get beta 2 plus beta 3 times x2. So if x2 is equal to 0, dou y by, beta 3 x1. If x1 were equal to 0, dou y by dou x2 will be equal to just beta 2. So this was where the square foot is 0, change in price by change in rooms will be beta 2. Well, now we have reparameterized. So delta y, dou y by dou x2 is given by this expression. So now dou y by dou x2 will be equal to delta 2 if x1 equals mu1. And therefore x1 minus mu1 will be 0. So we are now isolating that delta 2 in a much more meaningful way. If x1 were set at its average value, then delta 2 tells me the marginal effect of a change in x2 on y. If we were to retranslate this to the price in square foot example, if we were looking at a house whose square foot was equal to the average square foot in the sample, for such a house, an extra bedroom will increase the prices by delta 2. So if we were looking at the case where the square foot is set at its average value for a house with square feet equal to the average square feet, then an extra bedroom will increase the price, will change the price by delta 2. And this is a lot more meaningful than it was earlier. And that's the advantage with reparameterization. So we now have a better interpretation of our parameters. And then we also have standard errors which are now available, which are now given to us at the particular mean values. I'll show you an example where it works. So we can now be talking about statistical significance of this delta 2 under the assumption that x1 is equal to mu1. We can talk about statistical significance of the effect of bedrooms when the square foot is equal to the average square footage. And all of these results are automatically given to us by the regression model. Let's see another example. So we're looking at how a student's attendance rate affects their final exam scores. So final exam scores are dependent on attendance rate, previous GPA, a few other test scores, GPA square, see there's a quadratic term there, test score square, and an interaction term between previous GPA and attendance rate. Now, how will we interpret the effect of attendance rate on the final test scores? If we were to focus just on this coefficient, it means that if attendance rate increases, it leads to poorer test scores. There's a negative sign there, which doesn't make sense, right? Also, that interpretation will hold true only when this previous GPA is set equal to 0. Remember, dou STND final by dou attendance rate will be minus 0.0067 plus 0.0056 times previous GPA. So if previous GPA is 0, an increase in attendance rate will depress your test scores. But previous GPA being 0 doesn't make sense. And that's also not a realistic case. Suppose we look at the effect of attendance rate when, for an average GPA student, when average is say 2.5. If you plug in pre-GPA to be 2.59, then the dou y by dou attendance rate turns out to be 0.0078. So if you do plug in previous GPA is equal to 2.59, you get this answer. So for a student who's performing at the average level, whose previous GPA was the average score, if their attendance rate goes up, then their performance in the final exam goes up. This is a different interpretation to what we had earlier. Now, how significant is this statistically? Well, for that, I need to know the standard error of that estimate. But I can't find that from the regression that we have run on the slide here. So, in order to comment on the significance of this number, 0.0078, meaning what's the value of increasing attendance rate for a student who's performing at the average GPA level, I need to rerun my regression where I redefine this pre-GPA variable as pre-GPA minus its average. So I redefine the variable and I multiply that with my attendance rate. Notice that I'm only redefining the variable which shows up in my partial effect of interest, right? Previous GPA shows up in my dou y by dou x. So I'm just going to change that variable because that matters only that is sufficient for the interpretation I need now. So when I redefine and run that regression, the coefficient on attendance rate will now tell me the marginal effect of an increase in attendance rate on my final score, holding the previous GPA at its average level. And that coefficient will exactly be 0.0078. And now we'll also have standard error of that variable with us. And we could go ahead and do a joint hypothesis test to see if attendance rate is a significant variable at all. And for that, we can just do a joint hypothesis testing. And this is the benefit of reparameterizing your interaction terms. Just the final thought that I'll leave you with here. So when we computed all of these partial effects, right, when we were just taking dou y by dou x1 or dou y by dou x2, we saw that whenever there's an interaction term, that partial effect will depend on the value of that interaction term. Based on different values that you plug in for that, so here in this case, our partial effect of attendance rate was given by this expression. For different values of previous GPA, we'll get different results. If GPA was at the average level, you'll get a certain result for attendance rate. If the previous GPA was exceptional, you'll get a different answer. If it was very abysmal, you'll get a different answer. So the point is this partial effect will vary for different values of GPA. Oftentimes, we're just interested in some average measure of this partial effect. We don't want to be looking at partial effect at different values of your variable. It's just confusing. So the simplest and straightforward thing that we do is just freeze that previous GPA at its average level. That is exactly what we've been doing so far in our examples that I described. And there is a term for that. It's called the average partial effect. So when you're computing your partial effect, if you freeze the value of that varying variable at its average value, you get the average partial effect. And the particular type of reparameterization, it's also called centering values about their sample means. Okay? So that particular type of reparameterization will automatically force your coefficients to reflect the average partial effect. Go back to the previous slide and see how that 0.0078 number comes up when you actually plug in the average value as well as when you reparameterize the regression. So that's called the average partial effect. So this is often done, but when you have larger and more complicated models, this process becomes tedious. Thankfully, our softwares have a lot of very convenient workarounds, which allow us to compute partial effects, average partial effects, and compute their significance as well. So that wraps up the section on models with interaction terms. So I'll see you in another video to talk about the next topic.